follow the car. In this exercise, we'll try to implement a controller so that a car, represented here, has to follow another car, this one. For this, we'll decompose the problem into two parts. The first part, we'll find a controller for a double integrator given by the differential equation y dot dot equal to u, where u is input, y is the output. And for this, we'll use a proportional and derivative controller given by this. We'll have to find the coefficient k1 and k2 in equation 3 so that the error will converge to 0 in an exponential manner. So the poles will be equal to -1, which correspond to a constant time constant equal to 1 second. And in the second part, we'll consider the problem where we have to follow the car in an autonomous way. So question number 1, I consider this differential equation, this one, which corresponds to an integrator like this, another integrator like this. I have here u and here the output y. So we'll first give a state representation for this. So the state representation is given by x dot 1 it equal x2 and x dot 2 is equal to u. So it means that here I have x2 and here I have x1. Okay, and the output is y equal to x1. This corresponds to a state representation. In a matrix form, I have x dot equal 0, 1, 0, 0, x plus 0, 1, u, y equal to 1, 0, x. We propose a proportional and derivative control given by u equal k1 w minus y plus k2 w dot minus y dot plus w 2 dots like this. It is a controller we propose for my system. Now my system is this one. Y dot is here, correspond to x2. So if I assume that the state is available, I have here x2 or y dot, and here I will have y that I need. And w of t is known and correspond to the set point, to the output I want for y. And this will compute u. It is a classical proportional and derivative control that we use when w depends on time, as it is the case here. So in question 2, we'll explain why this controller is nice. Because if I consider the error w minus y, I will show that E satisfies a differential equation which shows that E will converge to 0. Since y dot dot equal to u, which corresponds to the double integrator differential equation, I take this expression for the controller and I obtain y dot dot equal to k1 w minus y plus k2 w dot minus y dot plus w 2 dots. Now this corresponds to E. This corresponds to E dot. And if I take this one, I put it on the other side, I will have W dot dot minus Y dot dot. Here I get 0, and this corresponds to E dot dot. As a consequence, I get the differential equation for the error, which tells me that Y dot dot plus, so K1 E dot, okay, so here I will take K1 and here I will take K2, plus K1 E dot plus K2E equals 0. And this differential equation does not make appear variables such as u and y. The error is totally independent of the other quantities. So I will find now the K1 and K2 so that this system is stable, so that E will converge to 0. Question number 3. The characteristic polynomial of this differential equation is P of S equal S2 plus K1S plus K2. And I want the root of this polynomial equal to minus 1. So for this, I will choose here S plus 1 square, which is equal to S2 plus 2S plus 1. By identification, I see that this one is equal to 2 and that this quantity is equal to 1. As a consequence, K1 equal to 2 and K2 equal to 1. On the second part of the exercise, I consider a tank-like vehicle described by this equation, correspond to this vehicle in the picture, and we have to follow another car. So exactly we have to be on a virtual point that is on the back of the front car. So we assume that we are able to get from the previous car to know the state variables that are assumed to be known exactly. So we consider the state x, y, theta, and v of our robot, and we have to show that the second derivative of the position x and y of the robot can be described by a matrix which depends on x times u, the input of the system. Okay. Then, on the second part, we'll try to find the controller to follow the previous car. So this is our system where x and y are given here. For the first question of the second part, so part 2, I have x dot dot 1 to express, so I derive this first equation and I obtain that it is equal to v dot cos theta minus theta dot v sine theta, and y dot dot is equal, so I derive this one, and now you obtain v dot sine theta plus theta dot v cos theta. So v dot corresponds to u2, so this one is u2, this one also, and theta dot correspond to u1. Thus, I obtain in the matrix form x dot dot y dot dot is equal to minus v sine theta cos theta v cos theta sine theta multiplied by u1 u2 is correspond to the matrix A of x, where x is a state vector which is composed by x, y, theta, and v, and this one is u. For the second question, I have another mobile vehicle that I have to follow, as in the figure. So on the back of this of the front vehicle, I have a virtual attachment point, and I want the center of my robot be exactly at this virtual attachment point. So the idea for this is first to find a controller to perform a loop which gives me of this form, where Q is a new input. And with this Q, we'll see that I have a double integrator, and I will be able to use a controller that I have obtained in the first question. So that's what I will do. Since I have this equal to a of x times u, the idea is to get rid of a of x by taking u equal n minus 1 of x multiplied by the new input q. So if I do this, since u can be chosen as I want, indeed, this is my system. And if I take u equal a minus 1 of x times q, so it's some kind of controller. I have q as a new input. The state x comes from here, where x is given there. And I have this. And if I apply this, this is my closed loop system. Okay. And with this controller, I will have a simplification between a of x and a minus of x, and I will obtain x dot dot y dot dot equal to q1 q2. So it is a question number 2 of the exercise. Okay, so it means that and q1 q2 can be chosen as I want. It is my new input. So this corresponds to, if here I have q1 and q2, I have a double integrator which generates x and a double integrator that generates y. And I know how to control this one. I know how to control this one. Both are decoupled. So for this, I will use what I have obtained in the first part of the exercise. Now, what about so for this, for Q1, due to the first part of the exercise, I will obtain xa minus x plus 2x dot 1 a minus x dot plus x dot a, where here xa plays the role of the w of t I had for the first question. It is what I want for x. So it is a proportional and derivative controller. And I will do also the same for Q2. Q2 will be y1 minus y plus 2y dot a minus y dot plus y dot a. Now I know that x dot, so the value of x dot and y dot are given here, here and here. So this corresponds to v cos theta and this one to v sine theta. So I know u with respect to x and q, and I know q here and here with respect to x, and the desired position I want for my robot will correspond to the attachment point. As a consequence, the resulting controller is u1 u2 is equal to, so I take the matrix x of a of x, which is this matrix minus 1, and I will multiply by q1 q2 . This is for the x part. So this is my controller. If I take my robot here, I take my controller, which will feed my robot in order to compute the acceleration and the rotation rate from the previous robot, which is here. This one will give me the position of the attachment point, which correspond to xa and ya. It will communicate to this robot, but inside this robot I have my controller. There is a computer inside the robot which receive the information of xa, ya, but also, since it knows its own rotation rate, its own acceleration, it will also give me the derivative x dot a, y dot a, x dot a, y dot a. Here, the controller will use this expression, and as a consequence, I know that this point, the error between my robot and this attachment point, E of t, which is a two-dimensional vector E1, E2, this one will converge to 0 with at a speed corresponding to exponential minus t, which corresponds to a constant time approximately equal to 1 second.